Right, so welcome everyone. Thanks for joining us. Today we have the pleasure to hear Lin-Qing Chen, who is a postdoc in Brussels at ULB, and she will tell us about recent work on Virasoro charges and entropy for axisymmetric Killing horizons. Please.
Thank you so much, Mark. I'm really glad to discuss some work we did in Parameter Institute last year. And it was really exciting for me, this topic. And so the talk will be based on these two papers. The first one started as the PSI winter school work with the PI student Wanzhen, Shuwei, Bruno, and the PI postdoc Anthony. And the second one is a follow-up work to just strengthen the result a bit. So we're all deeply curious about what is the microscopic origin of the horizon entropy, what are the degree of freedom responsible for it, and how can we define phase space and eventually the Hilbert space for those quantum states. Is that due to the presence of horizon as a boundary, part of the diffeomorphisms become the physical symmetry on the gravitational phase space. And the black hole entropy, the size of the Hilbert space, is governed by such horizon symmetry. So in particular, the approach I want to discuss today is by using Cardy formula, which has a long history and it is really a magic for me. I still do not quite understand why it works so well. So let us keep this mystery through the whole talk. So initially, the idea of using symmetry to constrain the density of the black hole microstate was realized in Strominger's derivation of the BTZ entropy by using the Brown-Hanau result of the symplectic ADS3 symmetry and the Cardy formula. And Cardy demonstrated that the idea not only work for the locally ADS3 black hole, but also for genetic healing horizon through analyzing the symmetry which preserve the near horizon RT plane. This work has been was done long time ago, but there's some issue with the work of they only get one copy of the Virasoro, and also there is some ACOC about the periodicity conditions. There are many subsequential work on the generalizations, and this derivation of microstate counting for extreme occur motivates the proposal for the Kerr safety correspondence. So I really personally like this approach. The reason is that it is very general and theory independent. It doesn't depend on which particular quantum gravity theory we are using, but it provides guidance and insights for quantum gravity. And also another reason is that area law in some sense is like ignorance of the UV gravitational information, and it represents a universality class. And one necessary condition of applying Cardy formula is the modular invariance, which provides an explicit high temperature, low temperature, or UV-IR correspondence. So I think this direction, there will be something very deep in it that I haven't seen yet. So the starting point of our work at that time was in the PSI winter school exactly a year ago, was starting from the this paper from 2018 by Haco, Hawking, Perry, and Strominger on the microstate counting of the Kerr black hole. So they designed the following coordinate transformation to bring out ADS3 factor of the near horizon region of Kerr. And this transformation was already designed in this hidden conformal symmetry paper. And they have the left and right CFT temperature, which is inversely proportional to the spin, and the central charge proportional to the spin of the black hole. However, there are many questions that we found very unsatisfactory. The first is that there's really the zero spin limit towards Schwarzschild is really ill defined, as the temperature will blow up and the central charge will go to zero. Also in the paper, they have an unjustified Wald-Zoupus construction to make sure that finally the entropy counting works. And also personally, I'm curious the most is why this coordinate work, what this construction is geometrically. So then we could generalize it to, so by black hole rigidity theorem, all the black hole solutions on dimension larger than 3 is stationary, the horizon will be stationary, bifurcate, and asymmetric, with the horizon generator in the following form as the sum of the stationary killing vector plus the horizon angular velocity times the asymmetric killing vector. And this A indices is in case there's more than one rotational direction. And so the mutually commuting vector fields in such a space-time could define the near horizon Rindler coordinate system. So these mutually commuting vector fields are the horizon generator, the asymmetric killing vector, and another radial vector which was defined in Cardy's paper in 1999 is basically in this form of chi-square is the norm of the horizon generator. So this radial vector will be same as the horizon generator when it is taking the horizon limit. And so spanned by such commuting vectors, we will have the near horizon expansion written in this Rindler form. So here I want to emphasize that we choose the phi to be co-moving angle because later it really brings out this geometrical character much more explicitly than usually people use on the Boyer-Linguist coordinate of curve. So with phi as the co-moving angle and x is the proper geodesic distance to the bifurcation surface, all such space near horizon space-time geometry up to the first order of the expansion is written in such form with our familiar Rindler piece. And this is the transverse direction apart from the rotational direction we are looking at. And with the angular momentum aspect and another possible can encode the angular momentum of other rotations or just a parameter.
Lin, can I ask a question?
Yes, please.
So here all your functions are allowed to depend on all the coordinates, I mean, on time and on the angles, right? Or
so here, next slide, you will see the explicit examples of what they are. So for every space-time, we can solve out. So x will be the proper geodesic distance to the bifurcation surface is time independent, and then n phi na will depend on the theta, and as well as the psi square is the norm square of the rotational killing vector will be theta dependent. And so for the theta case, in the usual short coordinate, we can solve out the x by the familiar tortoise coordinate at the lowest order near horizon. And then the transverse metric is simply L square, and we are not rotating, we don't have n phi and na. For curl, it's slightly more complicated. This x can be derived by taking the covariant derivative of the killing vector square. And then through that, you will construct, so the exponentials of the tortoise coordinate corresponds to this x. And
but these are for, I understand, for specific cases, they take certain value, but you will allow, I guess, a very generic phase space rather than restrict to some solutions, right? So in full generality, what do you allow on the function? Like, do you allow them to depend on time, for instance, even though for Kerr they are just constant?
Yeah, that's a really good question. So in the situation we are studied, they are all not time dependent. All x and phi and na, they are only a function of theta and the radial data. And in general, one could consider even the time dependent kappa. I think that was actually in your work you studied this part, and that would be interesting as considering dynamical horizon or like near abatic situation, rather than just like a state.
Thank you.
Yeah, it would be really interesting to look at the time dependent part. However, for this work, later you will see that all the construction is just near the bifurcation surface. So we didn't do the time evolution along the horizon yet. And so the two Noether charge corresponds to the horizon generators, and the axisymmetric killing vectors are the area and the angular momentum. They are in this form. So the fun part is really design this conformal coordinate inspired by previous Strominger, Haco, and Hawking and Perry's work. So it's actually in a very concise form that you can express the W plus W minus and Y coordinates simply as this classical coordinate times a phase. And this phase, the functionality, in my view, is like it is like a lens to zoom in this near horizon region, like the exponential of phi. And this Y is just the exponential of this angular co-moving coordinate. And because of the periodicity, we have to identify the points around every 2 pi. W plus minus Y will have the periodic identification. And this part is the same as the previous work on this periodic identification. And with this such a conformal coordinate transformation, this stationary axisymmetric killing horizons metric will be recast into a form that at the leading order piece is a locally ADS3 in the Poincare coordinate. Well, the ADS3 radius is a theta dependent function given by the psi and this free parameter alpha and beta. Later will be related to the CFT temperature. And the whole metric will have the higher order correction as we go slightly further from the horizon. So W plus W minus will be 0 on the bifurcation surface and on the horizon. So this will be the first order's contribution. And so here, there is a picture of just indicating how this strange coordinate system looks like. So the orange spiral and blue spiral are all both fixed W plus, and how they intersect with the stretch horizon, which is a fixed X hyperbolia, and the constant T, which is this green surface. And because they are plotted in the same value, so they cross at a point and spiraled differently along the two hypersurface. And they all correspond to a same W plus value. So it's like a spiraling coordinate on the space-time and becomes the Poincare coordinate on the ADS3, where W plus minus are like the Rindler coordinate on the boundary of ADS3, and Y is the radial direction of the ADS3. So the ADS3 folia help us to write out the Brown-Hanox vector field in this coordinate, in this Poincare coordinate, the Brown-Hanox vector field has the following form. This was used in their paper. And the mode expansion from the periodicity conditions is defined in the following way. Then the Lie brackets of the vector fields form with algebra. So I want to emphasize that they have singular limit when the coordinate W plus W minus goes to 0. So more precisely, one copy of the algebra are regular on the future horizon, but not on the past horizon. The other copy is regular on the past horizon, but it has singular limit when you approach the future horizon from the past horizon. And so the Franz-Thorn vacuum density matrix, which is a density matrix like close to the near horizon space-time, it is originally written in terms of the energy mode corresponds to the killing vector. And so now it can be expanded as the 2-piece corresponds to the 0 mode of zeta and Xi, because the 0 mode of this Witt algebra is just a linear combination of the killing vector. So then one can define the left and the right energy mode corresponds to the Witt algebra respectively. and recast the Frost-Thorne vacuum density matrix in this way. And later it will relate it to the dimensionless putative CFT temperatures, because it's also defined the periodicity on the two torus. So I want to comment a bit more to get some more geometrical intuition. So the first question is, which structure this weight vector field is preserving? Because this is kind of a different logic as usually we study asymptotic symmetry. We define what's the structure we preserved and we solve what's the vector field for it. But here, in our investigation, we directly use the Brown-Hanel vector field. Then why it works so well, we come back to understand it later. So the diffeomorphisms preserves the nullness of the horizon. However, both surface gravity and horizon generators are violated by this field variation or point wisely. And so actually in the follow-up project, one of our student collaborator, Bruno, figured out that, so originally we know that the weight vector field is just preserving this piece of the asymptotic ADS3 metric, this leading piece. And actually this leading piece is a part of the leading order of the Killing tensor. More precisely, is the Killing tensor without the R squared G mu nu term. And the Killing tensor, we know it plays a substantial role on the hidden symmetry of a test field on the spacetime. So this can draw a precise link between the asymptotic symmetry on the gravitational phase space and the hidden symmetries of the test field on the black hole spacetime. And then another point I want to emphasize is there are two boundaries in the story. This is very interesting for me. The first boundary is the boundary of our Cauchy surface. It's our bifurcation surface, which lies at W plus minus equal to 0. However, our asymptotic boundary of the ADS, which should be the y goes to 0 limit of this ADS3 folia, it does not necessarily live at the spatial infinity as the usual in the curve CFT, you have the infinite long throat. The boundary is really at the infinity. Here is a bit different because our y does not have the radial dependence of the parameter. So what actually plays the role of a radial direction is this co-moving angle phi. Co-moving angle phi can run from minus infinity to infinity, and every 2 pi is like a fundamental domain for its value. However, the precise value is a gauge choice. And when phi runs to minus infinity, mathematically, it actually reached the asymptotic boundary for this ADS3 folia, which I think is really interesting. And so here, there's another plot of indicating that although the bifurcation surface is precisely lies at W plus, W minus equal to 0, however, any finite value of W plus minus can go arbitrarily close to the bifurcation surface. So those spirals are fixed. So with both these two fixed and how the intersection of the hypersurface goes in the space-time, and it's all looping into the bifurcation surface. So after we have the geometrical construction and the symmetry we want to consider, now we need to realize the symmetry on the gravitational phase space. So we're using the covariant phase formulation, which is a very beautiful formulation developed by this many people's work. And so we will use the pre-symplectic form associated with a Cauchy surface with boundary. And the diffeomorphisms, which are pure gauge, corresponds to the degenerate direction of the symplectic form. The non-trivial part will correspond to a Hamiltonian, which generates the symmetry, or in other words, the large diffeomorphisms on the gravitational phase space associated with this vector field. And by the Ayer-Wald formula, the Hamiltonian can be solved by inserting the field variation as the Lie derivative of the G mu nu. And then the two pieces, one is a comma charge in the gravitational situation, and the other piece is the interior product of the vector field into the symplectic potential. And here we use the slash notation, follow the literature, because to emphasize that it's very non-trivial to make this charge integrable. And by the charge representation theorem, if the Hamiltonian is indeed integrable, then the realization of the Lie bracket of the vector field will be realized as the Poisson algebra on the phase space up to a central extension. And in our case, when it is Witt algebra, there is a unique non-trivial central extension gives the central charge. I also want to emphasize that the meaning of the charge is integrable in the sense of so the delta H, this form needs to be an exact form on the field space. One can check it by do another variation to see whether gives 0. And only it is an exact form can we say that the integration on the field space will be path independent. Let's say we start from reference geometry and want to solve the Hamiltonian to a targeted geometry with some perturbation. Then only when it is an exact form, this does not depend on which path I'm going on the phase space. And also a few more words on the central extension. So it measures the Poisson bracket on the phase space fail to represent the Lie algebra of the vector field. And explicitly, it is given by this formula with the interior product into the symplectic potential and plus with the Lagrangian part. And this doesn't contribute in our scenario of analysis. So it is a Casimir on the phase space, does not generate flow by itself and forms the two cocycles on the Lie algebra of D field. When the Hamiltonian is shifted by a constant, so this is actually very important because the symplectic potential can have the various types of the ambiguity. So when the Hamiltonian is shifted by a constant, the central extension also gets shifted accordingly. So to really well define those Hamiltonian, we need a closer look at the null data. So for any special cross-section of the horizon following the light ray, we have the two null normals or vector fields. So the induced metric on any cross-section of the horizon can be expressed as the space-time metric minus the two null normals. And the barred one here is indicating the transverse to the horizon, and the unbarred one is the one that's along the horizon. So the normalization, this is a normalization of convention to fix the parallel and transverse, these two null normals to be a constant, but it only fixes those null vectors up to a rescaling of arbitrary function. And those functions, I think in literature, it might have called a boost gauge. It's like a gauge freedom of how you choose the null vectors. And so in this work by Florian and Lohan, because they were studying in detail of the structure of the symplectic potential, they realized that if you write these null vectors in the following form, it has a lot of convenience later to decompose the symplectic potential. More precisely, they define like a covariant derivative. It is a covariant derivative on this codimension 2 sphere, and this A will be a one form in the normal plane of S and evaluated into the tangent space of this 2 sphere. So in our near horizon expansion from the metric data, you can read out what is those connection are, and so they are ordered at the order of x squared. And so on the horizons, then the generator will have the following form, and it becomes the this part is written in terms of the familiar classical coordinate. So the advantage of defining this way is that then when look at the symplectic potential decomposition, every term is by itself the boost gauge invariant. So every piece of the symplectic potential will be invariant under this arbitrary rescaling of the function. So then the weak vector field on the horizon on the null hypersurface can be expressed as this null generator and this axisymmetric killing vector. So then we can see that on the horizon, it generates a U-dependent translation and also a U-dependent rotation. And it has a singular limit when U goes to, take the limit towards U goes to 0. Then to study the phase space symmetry, we need to look at its variation induced by the diffeomorphisms, which is defined in this way. It's like any tensor, any space-time tensor, you take partial derivative of the metric and times the Lie derivatives of so it will be the delta GAB. And we need an extra assumption on what's the reference point of this variation. It's on the phase space. If I'm looking at the delta G or delta some tensor, what's the reference point of things that are not moving? And so here we assume that the variation of the horizon generator along itself, so along the null direction, does not change. So it corresponds to a fixed time foliation on the horizon. And one can also fix a different structure. And in another follow-up paper done by Anthony and Van Chandrasekaran, they fix a different structure as a covector for analyze the phase space. And then the various field space variation, the result of the quantity will be different, but finally the observable will be the same. So then we can see that the variation of both null generator and surface gravity are non-trivial. And interestingly, as was originally shown in the in Strominger, Sasha Haco and Perry and Hawking's paper, that it is the pole in the diffeomorphism when you take the limit towards bifurcation surface, when this pole is responsible for the existence of central charge. And so this coefficient is exactly proportional to this pole of diffeo as the field space variation of the null generator. So now with all those field space variations, we are ready to look at the null symplectic structure. So we'll be using the symplectic potential from Einstein-Hilbert action with cosmological constant, with adding a piece of the null analogy of the Gibbons-Hawking-York boundary term as a kappa times the horizon form density. And so I will be applying the result done by Florin and Lohan on recasting the symplectic potential into a very neat form, in the sense that when it written as a P delta Q, the configuration variables are only in terms of the intrinsic geometry of the null hypersurface, while the conjugate momenta are extrinsic quantities. So they recast the symplectic potential into this whole piece is the flux piece, and it has the spin 2 part, which is the shear tensor with delta of the conformal metric, and the twist part, which measures a surface twist inside the horizon if we let it move along the integral curve of L. So this is the spin 1 part, and the spin 0 part, which is a kappa and the expansion with the trace of the delta Q, while Q tilde is the induced metric on the two sphere. Then we also have the total derivative, an exact piece of the symplectic potential, which comes from the boundary term you add to the Einstein-Hilbert action, and also some corner term. And the corner term, which is usually very important in the analysis, and in our case, because at the end, it didn't shift the central extension, so we do not show the form of it here on the slides. And the twist 1 form on the horizon can be evaluated very simply as this angular momentum aspect and the other piece. And for the killing horizon we are looking at, because it is shear free and expansion free. So then the symplectic potential will be simplified a lot. Then to have a well-defined Hamiltonian and any cross-section of the horizon, we need to examine whether this piece is a field space exact form. So apart from the gamma charge part, we need to look at whether this interior product into the symplectic potential, how it looks like. And the interior product will naturally, because of the feature of this weight algebra, it will encode a periodic exponential of Im5 for every modes. So we could make use of this feature in the integration, because to have a well-defined Hamiltonian is a bit non-conventional here, because as we know, the field space variation make a delta kappa and a delta L non-trivial every point wisely. So if one impose a boundary condition to annihilate all those obstruction terms, it will actually annihilate the symmetry as well, because the weight algebra wouldn't allow those variations to vanish. However, on the other hand, it can impose in a weaker form, in the sense of if we require the symplectic flux integrated along the transverse direction on this codimension 2 sphere to be an axisymmetric function, then together with the integration of the exponential, it will make this whole piece vanish. So
what is eta in here? Eta, what is it?
Oh, so eta here, it was from, it's a coefficient. Okay, here I should emphasize more. On the action I'm looking at, for the boundary term here, I add a free parameter, eta.
Okay.
So this will be a number, just a number of how much of the boundary term of the action I'm adding in. And usually this should be determined by well-defined variational principle of what the boundary term should be. And later we will see that this value of eta actually plays an important role, and it is still quite mysterious for us.
It's like the choice of your corner, or is?
You can recast this piece to the, so this will be a boundary term of the Lagrangian, and on the symplectic potential, it will be an integration along the whole horizon. It will be a kappa times the volume form of the horizon, and the eta is a number times that, and it corresponds to the Lagrangian have a kappa epsilon term. So because the horizon is the boundary of this whole M, oh, sorry, I should have explained here more explicitly. This M is our whole spacetime I'm looking at, and the boundary of it is the horizon, and with the extra piece of the boundary term.
Thanks.
And Lin-Qing, I have another question, please.
Mm-hmm.
So if you go to the next slide.
Mm-hmm.
So, but the vector fields that you're considering here, the xi-m's, don't they also depend on the data that you're varying on the fields?
Okay, that's a really good question. Here we assume the all the weight vector field is field independent. We assume they are not varying, but when it's very interesting to consider how it varies, because the zeta will explicitly have the surface gravity information in it, and when surface gravity varies, it should vary. But one can also consider it as a background constant. So I think the simplest case, we are now considering the zeta are field independent.
Yes, but I'm kind of confused as to which, actually the algebra of which vector fields you're looking at, because the vector fields that preserve the geometry that you fixed, I think they will be field dependent, right? Can you actually consider them to be independent, or?
So here the zeta, the weight vector field one is only preserving that leading order piece of the asymptotic ADS3 folia.
they don't preserve the geometry, right? That's the whole point.
They don't preserve they only preserve the horizon being null. They don't preserve surface gravity or horizon generator, and they preserve this piece of the metric tensor, which is the leading order piece of a Killing tensor, minus R squared G mu nu term. Or in the ADS3, this will be the ADS3 Folias metric, and so you take a lead derivative of this whole piece. The cross term will have a contribution into the leading order, and the only piece that's invariant by itself is the leading order piece. And I fully agree that for thoroughly analysis, one should consider the weight algebra is also field dependent. And in that case, the algebra will have a modification on the field dependent part.
Mm-hmm. Thanks.
Mm-hmm. Thank you for the question. And so if we impose such a boundary condition to require the symplectic flux to be axisymmetric function, on the future and the past horizon, it will be imposed as the following condition. When it satisfies at the same time, strangely, it determines that the boundary term of the Lagrangian we need to add in it has the following coefficient. And it also confines the alpha beta to relate with the spin and the area of the horizon. So there are a few ways to look at it. From the hard mode, from the flux perspective, it tells what's the flux is allowed, which isn't the most generic case. It is more like I'm looking at outside of the horizon, as like in a box, and fix certain boundary condition of what kind of flux I'm allowed to make sure my Hamiltonian is still integrable. Because the question we are looking at is the density of the state, it's the entropy aspect. And then on the other hand, it also selects out what's the class of the weight vector field, which is parametrizing by the alpha beta that we are looking at. It also selects what's the ADS3 folia that is allowed for the integrable situation. Because we recall earlier, actually the ADS folias, the radius of ADS folia is inverse proportional to alpha plus beta. So the L is equal to the psi squared divide alpha plus beta. So every choice of alpha beta, it gives a unique choice of the ADS3 folia. And I also want to emphasize that this integrable situation, this will be very different. This will be a different pair of the temperature than the one used in the current CFT one. Okay, so now when we are sure that we can have a well-defined Hamiltonian, we can solve for the Virasoro charges. And apart from the zero modes, all higher modes integrated to zero on the cross section, and one could only write down its non-trivial density. It's the exponential of IM phi. We integrated on the codimension 2 sphere. This whole piece gives 0. And the difference of the zero mode, the L zeros, this part will be a linear combination of Noether charge. It's similar with the familiar situation in the ADS3. The zero mode generates the rotation. It corresponds to the spin of your space-time. And the central charge is proportional to the area of the horizon, the cross-section of the horizon. And it can also be recast into a form that's very close to, that is direct analogy to the Brown-Hanel central charge as an integration of the transverse direction of my ADS3 radius. So then assuming a unitary modular invariant 2D CFT interpretation, the entropy of canonical ensemble is given by the following form, and it reproduces the Bekenstein-Hawking entropy. And this could be done within the range of validity because we have a freedom on this alpha and beta as temperature. So another way of defining to well-define Hamiltonian is by using the Wald-Zoupus construction for the non-integrable charges. more precisely, it is adding a d-1 form to the symplectic potential. What it does is basically subtract the non-integral part, which is also the gravitational flux part. So to subtract this from the symplectic potential as a compensation of the gravitational flux going through the system. So then this delta becomes an exact form with adding this extra piece of the interior product of the flux in the symplectic potential. And then one need to use the Barney-Chasar bracket to modify it that's different with the Poisson bracket to calculate the algebra. And then the central charge will have a shift as the inverse to each other. And finally, the central charge will still proportional to the area. And this whole Wald-Zoupus construction, I'll reference to a comprehensive analysis later done by Van and Anthony. And so what they did is actually, if you have certain principle of fixing what is flux and what is to take the symplectic potential, because there's ambiguity of you can add an exact form in terms of space-time exact form and field space exact form. And if you fix the flux based on certain principle, then actually at the end you get was the central charge is double the answer. So it will get the entropy counting as double of the integrable case. And for the non-integrable charge analysis for this more generic open system of considering flux going through the horizon, see also the work and etc. This is just only two recent works. And so in summary, we studied the stationary bifurcate healing horizon with axial symmetry in D larger than 3, and which are basically black hole rigidity theorem tell us this includes all the solutions for black hole horizon. And the general construction also directly applicable for Rindler space. And so the gravitational phase space admits the 2D conformal symmetry algebra with central charge proportional to the area of bifurcation surface. And this is different with the previous work result as the central charge proportional to the spin of the curved black hole. So then it allows us to have the well-defined zero spin limit to Schwarzschild. And one advantage is that this construction also allows the CFT temperature to be chosen within the validity range for the Cardy formula. Because in the previous, in the current CFT scenario, the pair of CFT temperature is completely fixed by other physical reasoning that we could discuss later. However, once the temperature is fixed, the Cardy formula is not applied within the range of the validity. And so since this cardiology strangely works, it suggests a microscopic interpretation as a 2D CFT for any dimensional killing horizon, which we will discuss later. I think that will be a very interesting point. So here are the following questions. Some are my concerns, some are open questions, all the things I'm very excited about. So the first point is that each copy of the Virasoro generator is only defined on each horizon respectively. So on the future horizons, that copy of Virasoro, you take the limit towards past horizon is a singular limit. However, the Cardy formula is applied on the bifurcation surface. But we don't have two copies of Virasoro simultaneously. We only use the central charge result that would agree on the bifurcation surface and then apply the Cardy formula. So this is a very non-satisfactory point for me. So probably we need to define the quasi-local charges on the stretch horizon to look at a bit away from the bifurcation surface to see whether the two copies of Virasoro can coexist. And then the question I'm curious the most is why this works. So we know that a necessary condition for applying Cardy formula, so not only this Virasoro version of Cardy formula, also there's a chiral version, warped BMS3 version, has all historically been shown as examples that reproduce the right entropy counting. However, all those related symmetries, to prove the Cardy formula for those symmetry, you all need the modular invariance for the CFT, which provide an explicit UV-IR correspondence. It will be extremely interesting to work it out. Where is this modular invariance on the gravity side? So we know that generically, we already have the two characteristic circle of the two torus, which will be the time, the t cycle and the phi cycle. And the t cycle here, we need to do a past future identification. As it's a stationary space-time, there's a Killing vector, and one can easily do such an identification on the Euclidean path integral. And the phi is our natural asymmetric, corresponds to the asymmetric Killing vector. And different with the ADS3 case, if one want to do the modular transformation on the gravity's partition function. So different with that case is here we have the transverse direction, which available if we perform the S transformation to swamp the circle. I do not know the answer yet, and I think that will be really, really interesting to work out how exactly, like whether we could have such a symmetry on the near horizon gravitational phase space. And then it leads to this question immediately is what's the precise relation with the Euclidean path integral derivation? So in the originally Gibbons-Hawkins Euclidean path integral derivation, the non-trivial part of the partition function is concentrated on the boundary term. And so in our case, this boundary term of the Lagrangian also plays a very crucial role, and especially it shows more explicitly in Van and Antony's paper that they fix a different structure than here I'm talking about. And with fixing a different structure, they concentrated the whole anomaly on the boundary term of the action. And another question I'm very curious is that we only make use of the 3D folia, and we also this is only a subclass of the full symmetry that Killing horizon could have. We completely didn't touch the additional rotational symmetries. It seems all irrelevant because the 3D folia construction is only based on this xt phi direction. And is that a signal of dimensional reduction? Also, the sign of dimensional reduction, we've seen it in many places, such as the central charge is an integration of those transverse direction, which theta all the other angular dimension apart from the rotational axisymmetric part. And also, if you could remember, the weak boundary conditions is also integrated along this transverse direction. So there seems a sign of the dimensional reduction for the near horizon quantum gravity. And the more ambitious proposal would be, what is that possible to have a near horizon CFT duality? And what type of CFT would be? What are the observables we need to check to justify such duality? And I think there's many experts in the audience, and I would be very grateful if you have some free feedback and a suggestion into this direction that I'm super interested in. And then related with this near horizon CFT dualities, these lines of thought, and what's the physical criteria of further specifying the CFT temperatures? As the integrable conditions, it's only a linear combination and it still have a lot of freedom on TL and T, right? It doesn't specify the precise value like the one in the current CFT. And so actually now we are having an ongoing work with in this collaboration on like relating the hidden symmetry of the test field on the space-time background and the cross-section of the test field to relate it with the CFT data to justify that whether we could really allow the freedom of the temperature that's still able to match with the CFT data. And the next question would be, what kind of physical process will implement Virasoro here? As we know that sending a shock wave into the horizon could implement super translation here, and it will be interesting to see what's the real physical process could implement this Virasoro hairs. And then the next interesting question is, actually there are two types of anomaly in the story. One is the conformal anomaly, our central charge. The other is the gravitational anomaly, actually would correspond to this Wald-Zoupus counterterm. And it usually encodes the lack of the diffeomorphism in the ADS block. And so when the system has a gravitational anomaly, the central charge, two central charge will not be equal, but it will be different with the exact same value. So the Wald-Zoupus construction here actually could be recast into the formulation of the gravitational anomaly as a transverse integration of those symplectic flux. That will be also interesting to study. And then final question is the construction as an entropy counting approach probably would be nice to generalize to more generic situation as arbitrary cut of the horizon or causal diamond. So since that right now the construction is centered on the bifurcation surface, as Laura suggested earlier, it would be really nice to consider a time-dependent evolution as a dynamical horizon. Okay, thank you.
Thanks, Lin-Qing. All right, so we have time for some questions.
I have a lot of questions, but I don't want to monopolize the...
You can go ahead, please.
Okay, so first, maybe, so what do they symmetry preserve then? This, you...
It preserves the metric tensor corresponds to the this piece, and then so it is actually the killing tensor. So killing tensor is a structure that is very crucial for the is responsible for the hidden symmetry for a test field on the space-time background. As so the integral of the motion is commute with the Hamiltonian, and then the Hamiltonian vector field corresponds to it. When you project to space-time, it will be like a momentum dependency. And so preserving this part of the space-time metric, so our student Bruno figured out that it's actually preserving this killing tensor minus R squared G mu nu term, which is the non-trivial part of the killing tensor. And I think that it is also actually preserve the principal null vector of the space-time, because the killing tensor can be written as the symmetrized version of the principal null vector, which is the eigen, the principal null vector come from the eigen bivector of the Weyl tensor of the space-time.
There are no hidden symmetries for Schwarzschild, right? Are they?
I think there is hidden symmetry for the solution, a scalar field, a test field for under certain near horizon approximation could form the representation, could form hypergeometrical function, then it will be like under presentation of SL2R. But I think it's only one copy of SL2R for Schwarzschild, and for Kerr it's 2 copies.
Okay. And you see, if I take different alpha, beta, different coordinates, so different alpha, beta, then I will, is it right to say I get a different central charge at the end?
Yes, so the central charge is inversely proportional to alpha beta. It's right. Alpha plus beta because okay, I think the other page might be more clear. Because the ADS radius is inverse proportional to it. So with the different alpha beta, you are just rescaling the ADS radius, and the central charge get rescaled correspondingly.
So that's very, I mean, how do you understand that? That depending on, you know, if you're supposed to be a universal sort of holography, principle?
So that's very, very important question. So for the, as you know, that in Andy and the Kurzweil, all these lines of work, the alpha beta was uniquely specified beforehand, including the asymptotic information of the Kerr black hole. So
yes, because they had the left and right temperature.
Temperature, yes, they are from the monodromy data of a scalar field on the Kerr background, including the whole asymptotic infinity, and it only even detect the inner horizon R minus information as the like 3 different pole structure for the Kerr. And then the temperature is uniquely specified by that. And so here we are looking at a different regime that we don't have so we only look at the near horizon renderer part, but you can still study the long wavelengths as you look, so you take the near horizon space and then take X and still goes to infinity. However, it does not detect the asymptotic flat region of the Kerr case. So I think it has less constraint compared with their work on this alpha beta. And so for this case, eventually, what we will need to justify is that the soft absorption cross section, like you send a scalar field on the Kerr background and calculate the gray body factor, whether this data could also match with the CFT 2-point function with the freedom of alpha beta. Because like for integrable case, it's a linear constraint, and with the Wald-Zoupus construction, alpha beta are completely free. So in this case, for the entropy counting purpose, there isn't constraint. And then the interesting question would be from the holographic consideration, whether it could be valid to get the match with the CFT 2-point function with the arbitrary temperature.
Does your construction admit a flat limit?
So you mean that a flat limit is, so here we can use arbitrary cosmological constant.
But does the algebra change in this case?
No, because the cosmological constant didn't come into the symplectic form. And we are only look at the near horizon piece. And so the cosmological constant only determines which on-shell solution we are looking at, but it doesn't change the algebras.
Yeah, I mean, the fact that it doesn't enter the symplectic potential is true, but it doesn't mean that the algebra will be independent, because
I would say that the cosmological constant will, because it determines which on-shell solution, it enters as my metric information, hence area, etc. But for charges, well, for the zero mode, certainly, because here I didn't write out explicitly, the zero mode is a function of area and spin. For higher mode, no, for higher, I think cosmological constant, I would say, only enters the charges as the metric information. It doesn't deform the algebra or like that.
So you're saying the algebra is exactly the same, whatever the value of the cosmological constant is, even when it goes to 0?
Yes, yes.
Because it's a near horizon thing, so it doesn't matter if your black hole is asymptotically flat or asymptotically antistellar.
And actually, it will be it's interesting in the sense of, if you send a test field to for the black hole, the monodromy data of this test field, the pole structure of the scalar wave equation will be like what type of pole, as it's regular, has a regular singularity or irregular. This will depend on your asymptotic boundary, as asymptotic ADS or asymptotic flat. But only for near horizon regions consideration, it doesn't matter.
And so you mentioned at the end that maybe you said that the Wald-Zoupus counterterm can be related to gravitational anomaly. Can you explain this a bit more? Because
yeah, so I think that point was actually originally in this in Paris Strominger-Hawking-Sasha's paper. They mentioned it already as if without the counterterm correction, your left and right central charge are not equal. And usually in the holographic system, unequal central charge means you have the gravitational anomaly. But then the paper didn't address how to precisely link it. And so here we know that the Wald-Zoupus counterterm actually is just the flux piece of the symplectic potential. It will always correct the central charge in the equal way. And this ADS3 folia is embedded in a higher dimensional spacetime. So we still have those transverse theta direction. And when you integrated this flux along this theta direction, so which is actually what the boundary condition annihilated, this part, it will, so in some sense, I think, so the picture I had in mind is that you have symplectic flux injected into the ADS bulk point at every point. And this injecting of symplectic flux are the integrated one along the transverse direction, because your ADS is the phi xt, only this 3 dimension. And of course, if you are injecting flux into the bulk, this breaks the d field invariant if you only look at the bulk. Hence, this, I think this counter term, or what the piece, the boundary condition is annihilating, can be probably recast as a Chern-Simon term that describe the lack of diffeomorphism in the bulk part of the gravitational partition function. And it will be very interesting to work out.
Can I ask a little question, Mark? Oh, yeah. Since you've already put a list of questions at the end of the talks, I just wanted to come back to the question about the physical process that excites the Virasoro here. I wanted to ask you, well, what kind of, if you have some ideas about these physical processes, and to which part of a metric would correspond exciting those Virasoro here?
So here, because the Virasoro charge can be described, can be defined on any cross-section of the horizon. So one could imagine sending something through the horizon, and it will be, in some sense, similar as the super translation, as we also generate a translation that's U-dependent. So I think there will be like an analogy to the super translation and super rotation, that's sending stuff into the horizon, and then the transverse direction of the, no, not transverse, the metric that parallel along the two sphere will fluctuate, and this part would correspond to like different point that generates by the Virasoro transformation on the phase space. However, the charge by itself, all the higher modes are 0. So one wouldn't be able to calculate a delta Q for it, but one could only get the delta Q as a density. So by density wise, it's non-trivial, but the expectation value of the charge is 0. And this is also analogic to previously in Laura's work about the symmetries of the horizon. Also have this property, I remember, in one of Laura's paper.
Yeah, and in another paper where we looked at the shock wave coming from past null infinity that hits Schwarzschild black hole, and yeah, this allows to turn on some super rotations here in the sense of what we call super rotation. So with our near horizon expansion, which is different from this one, but maybe there could be a way that you could turn on this Virasoro here, because for even sending from a shock wave that has a profile just along the time of VV components, then you can see that on the horizon it turns on super translation, but also super rotation charges. So maybe that might, yeah, there is a way to implant the Virasoro by such a shock wave process.
I suspect that so for each generator, when we send in a shock wave, this this connection part of the metric will all change, and the Q tilde will change. So yeah, that would be a really interesting thing to study precisely. Yeah, how does the sending in a shock wave, and what's the data on the metric part responsible for the implement of this Virasoro pair.
Okay, thanks.
All right, more questions?
If you have more questions, please feel free to send me an email and we can schedule some discussion. Because there are so many open questions I'm interested in and I don't understand.
Yeah, I mean, I might discuss with you once Mark closes the.
All right. So thanks again, Lin-Qing.
Thank you.